Hey folks, in this video we're going to do a short introduction to exponential functions. First, let's go back to the functions that we looked at in first semester. Those were linear and quadratic functions. In linear functions, we see that in their graphs, they're straight lines that have a constant slope, whether that's positive, negative, 0, or undefined. In the equations, we had three different forms. We had slope-intercept, y equals mx plus b. We had point slope, the one underneath it, and then standard form. With quadratics, we had a nice parabola U shape, either pointing up or pointing down. In the equation, we always saw an x squared. Here we have standard form, y equals ax squared plus bx plus c. We could also include factored form, y equals x minus p times x minus q. What makes exponential functions different than other functions we've looked at this year is that in the equation, the variable is going to be in the exponent position. And you could see that word exponent within the word exponential. Our equation in general is going to look like y equals a times b to the x power. So you see b is the base getting raised to the power of x. A we typically refer to as our y-intercept. It can also be thought of as the initial value. Often our a value is going to be 1. Next is the b value, and this is called our base. We are raising that base to the power of x, our input value. The base is going to control the general shape of the graph, and we break apart our exponential functions into two types, either exponential growth and exponential decay. What we're going to see is that if this base value b is greater than 1, then we're going to have exponential growth, in which our function is curved and increasing. Those y values are getting bigger as we go to the right. And we'll see that if our base value b is between 0 and 1, we're going to have exponential decay, which is where that curve is going down, or our function is decreasing as our x values get bigger. In both of these graphs, we're going to have a horizontal asymptote at y equals 0, and we'll talk more later about why this happens. There are many real-world uses for these exponential functions. Applications of exponential growth include populations growing over time and rumors spreading. Applications of exponential decay include medicine in your body that will decrease as your body breaks it down and processes it, and the value of a car that's going to decrease over time as it gets used more and more. Next, we're going to create some exponential graphs, and we're going to use some parent functions that have an a value of 1. So we're really just looking at the base raised to the power of x. First, we're going to start with y equals 2 to the x power. To create the graph, we're going to use a table, and we're going to use some small x values close to 0. I'm actually going to start with my x value of 0. Anything to the 0th power is going to be 1, and that's going to create that y-intercept at this point 0, 1. If I continue to fill in my table, 2 to the first power is going to be 2. 2 squared is going to be 4. So I get a few more points to add. 1, 2, and 2, 4. If I go into the negatives, 2 to the negative first power, I have to remember my properties of exponents. That's going to flip that upside down into a fraction. It's going to become 1/2. And 2 to the negative second power, that would be 1 over 2 squared, or 1/4. And you can see that as those x values go into the negatives, the y values are going to get really, really small. No matter how negative that x value is, though, our y value will not reach 0. Even if we had 2 to the negative 100th power, that would be 1 over 2 to the 100th power, which is going to be a very, very small number. The denominator will get really, really big, which makes our overall value really small, but still not 0. So as I connect my curve on that left-hand side, we cannot cross the x-axis. And as we get to the right-hand side, our y values are going to get quite large. Because our function cannot equal 0, we're going to have a horizontal asymptote at y equals 0 that tells the person looking at our graph that our function will never cross the x-axis and it will never touch it. Next, we're going to look at our function with a base value of 4, so y equals 4 to the x power. Again, I'm going to use our table. We're going to start with an x value of 0. 4 to the 0th power is 1. So you'll notice that same y-intercept at 0, 1. 4 to the first power is 4. And 4 squared is 16. So we can see this one is growing much faster, and that last row in my table actually doesn't fit on my graph. If I tried to plot a y value of 16, it'd be somewhere way up here. 4 to the negative first power is going to be 1 over 4. So we can see in the negatives, our y values get really, really small quite fast. 4 to the negative second power would be 1 over 4 squared, or 1/16, which is really teeny tiny. When we connect our points, we'll see that our curve is much sharper, that turn is much steeper, and just like with our base of 2, we're going to have a horizontal asymptote at y equals 0, because no matter how negative that exponent becomes, the y value will not be 0. Both of the graphs we looked at on the last slide were exponential growth graphs because our base was greater than 1. Here are some properties of exponential functions that have a base greater than 1. We're going to have a y-intercept at 0, 1. The domain is unrestricted from negative infinity to positive infinity. The range is going to be from 0 to infinity. Notice that 0 gets a parentheses, it's not included. Our graph is always increasing, meaning that our function's y values are going up as we go to the right. And we're going to have a horizontal asymptote at y equals 0. Next, we're going to look at exponential decay graphs. This is where our base is going to be less than 1. Our bases will always be positive. So you see here we have fractions that are positive and less than 1. Starting with y equals 1/2 to the power of x, we're going to use our table again. And I like to start with the 0 in the middle. Anything to the 0th power is 1. So you see that with the exponential decay, we have the same y-intercept that we had with our exponential growth graphs. Next, 1/2 to the first power is 1/2. 1/2 to the second power is 1/4. This time, as our x value gets bigger, our y values are getting smaller. Next up, we have our negative exponents. I'm going to kind of write this off to the side so I have more room. Negative exponents flip your base, so 1/2 to the negative first power would be the same as 2 to the positive first power, which is 2. So we have -1, 2. 1/2 to the negative second power is the same as 2 over 1 to the positive second power, so that's 2 squared or 4. When we connect our curve, you're going to see that now it's the right side that's approaching 0. But just like our exponential growth graphs, our exponential decay graphs will never actually reach that x-axis. So we're going to get a horizontal asymptote at 0. No matter how big the exponent becomes, our fraction will become smaller and smaller, but it will not reach 0. Looking at our base of 1/3, 1/3 to the 0th power is going to be 1. 1/3 to the first power is going to be 1/3. Anything to the first power is itself. And then 1/3 squared is going to be 1/9. Same y-intercept, and we can see that trend that as x gets bigger, y is getting smaller with this base of 1/3. Now for the negative exponents, 1/3 to the negative first power, we can flip our base and change to a positive exponent. We get 3 to the first power, or 3. 1/3 to the negative second power, we can rewrite as 3 squared, which is going to be 9. Connecting our curve here, we'll see that it's a much sharper turn than the base of 1/2. And we're going to add in our horizontal asymptote at y equals 0. Both of those graphs we looked at were exponential decay because that base was between 0 and 1. Some features that exponential decay and exponential growth graphs have in common is our y-intercept at 0, 1, the domain of all real numbers between negative infinity and positive infinity, the range from 0 to infinity, not including 0, and our horizontal asymptote at y equals 0. What's different about these graphs is that our function is decreasing. That curve is going down to the right instead of up. That wraps up our first lesson for Unit 12. You should try the homework and graph a few exponential decay functions and exponential growth functions on your own.